Greetings and welcome once again to my new calculus channel. My name is John Gabriel, and today I'm going to be showing you a very important video which I've touched on before, but people have asked me to go over again because they can't see how simple the video is. It's actually incredibly simple. So I'm going to take a bit of time doing this. So if you're in a hurry, now's not the time to watch this video. Just stop it and watch it later when you're more relaxed. Maybe grab yourself something to drink, hot beverage or an alcoholic beverage. Well, maybe not an alcoholic beverage, but you know what I mean. And then come and watch this video so that you can learn things that have never been taught to you at any school, at any university, and never before in the history of humanity have these things been written down. Because if they had, well, there's no record of it. So let's begin. So what is geoarithmetic? Okay. Geoarithmetic comes long before arithmetic. And who discovered geoarithmetic? It was a guy called John Gabriel. He's the guy speaking to you right now. He's a genius with an IQ above 160. So geoarithmetic, why is it important? And why should you even know about it? Well, let me explain something to you. If you don't understand arithmetic, you're not going to understand arithmetic. You're not going to understand fractions. Yeah, you'll know how to use them. You'll know how to add them, subtract them, divide them, do lots of fancy things. You might even someday know how to find solutions to partial differential equations. But you don't know anything about how the underlying arithmetic works, where it came from, and how to use it with understanding. Okay, so first things first. This knowledge was not invented; it was discovered. Just as all well-formed knowledge is discovered and never invented. Okay, and no, it was not written down by anyone else before me, and no one else even took the trouble to explain these things in ancient Greece, although I'm absolutely certain they knew about these things. It blows my mind that they didn't write these things down because you cannot understand arithmetic. I don't care if you're a Fields Medal winner or an Abel Prize laureate. You do not understand arithmetic unless you understand first geoarithmetic. Okay, so with all that behind me, I'm about to teach you these concepts, and I'll have you know that what I'm about to tell you is absolute truth. It's not research, it's not open to debate, it's 100% fact. No moronic professor decided that they were going to define it this way. Okay? They don't have the intellectual ability or the aptitude to even get close to that, even if they could live thousands of years. So, what is geoarithmetic? Geoarithmetic is the operations of arithmetic in geometry, okay? In other words, you're not using numbers at all. You don't even have a concept of number. You don't even know how to count, and you don't need to know how to count. All right? So, what helps us to do this? It's something called parallelism, okay? So, what is parallelism? Parallelism helps us to make these two different ratios where the vertical lines represent the antecedents and the blue lines the consequents. Now remember, I've told you in past videos that if you have a ratio like that or a line like that, you can only make sense of this line if you compare it to some other line, okay? Otherwise it's meaningless. And of course what you do is that. Okay, that's your ratio. Right. So what I'm telling you now is that This ratio here is indicated as the red vertical line and the blue line, and this one with the orange line, and the consequent, the brown line. All right. So they're two different ratios, and they're not equivalent because, watch, see there? They're not equivalent unless I make them equivalent. But I'll get to that in a moment. So if you join these points up here, these 2 points and these 2 points, those lines will not be parallel. But we cannot do anything with the operations of difference, which is the same as subtraction, or sum, which is addition, or quotient, which is division, or product, which is multiplication. We cannot do anything unless these ratios have the same consequent. Okay, the same consequent. How do we get the same consequent? So you can do it in one of two ways. You can either take a completely different consequent to both of these and convert both of them to that consequent, or you can convert this consequent to the brown consequent, or the brown consequent to the blue consequent. What I'm going to do is I'm going to convert the brown consequent to the blue consequent, okay? And the way I do it is as follows. I take a line joining these 2 points, like that, and then I position it on this endpoint here, and right over here where it crosses the red line, this little red section here is my new antecedent for this ratio, for the orange brown ratio with this consequent. In other words, it'll be this length to the blue length. That's exactly the same as this ratio here. Okay? So when I do that, I'm able to do a subtraction. And let's see how. So let's get that out of the way. So the subtraction says the difference ratio is the red antecedent, this entire red one, less the gold one. So all I have to do is take that away, okay, this part away, and the new antecedent is this red one, only the red one, to the blue one, okay? So this red and blue ratio, is in proportion now to the orange and brown ratio. And the result of the difference will simply be this red ratio to the blue consequent. Okay? Similarly, if we do addition, then the sum will simply be this part here added to the entire red consequent. So it'll be that, right? So this whole new antecedent to this consequent is the sum of these two ratios that you see over here. It's as simple as that. Okay? To get the quotient, what we do is we simply take this whole red line, which is the same as this gold line, to the new antecedent, which is this red line here. Now this red line here is equal to this orange line here. And this ratio is the quotient. It's the quotient ratio. Okay? That's all it is. Now multiplication is simply a reciprocal quotient measure. So instead of having the ratio as I did previously, like that, I just switch these two sides around. I make the brown the antecedent and the orange the consequent, like that. Okay? And then, of course, I take the quotient, and this here is my product, this ratio here. Okay? This ratio here is my product. It's just simply the entire red line to the brown line, which becomes the consequent. That's all there is to it. Now, you may say, well, what have I demonstrated here? Well, let me tell you what I've demonstrated. I've demonstrated all these operations to you without you knowing that. And by the way, let me just hide that for a second. It doesn't matter what the ratios are. Okay? It doesn't matter what the ratios are. I will always get the correct answer, right? What this means is that if you have a line segment, a ratio that represents phi, which is easy to get, as you can see in this video here. I'll show you how to get it without numbers. You can do perfect arithmetic with something like square root 2 or anything else. Anything else. You can multiply it by 5, divide it by 5. You don't need numbers. It's 100% accurate. You cannot do this in algebra because algebra uses the abstract unit to measure. Okay? So, this is what I've demonstrated. Now, to show you that I've demonstrated this, let's get some values. All right, let's move this out of the way. So we show the values, and let's make that. So this here is roughly 1 block, 2 blocks, 3 blocks, and this 1, 2, 3, 4 blocks, okay? But it doesn't matter because if you say 0.3 divided by 0.4, it's what? 0.75, isn't it? It's 0.75, which is 3/4. And this here, if it's if it's a half, it's just this orange line to the brown line, right? And of course, the difference is 1/4, because if we take the difference, right, it will simply be this guy here to this blue consequent. And as you can see, it's one of those to 4 of these, right? One of those to 4 of these. So it's 1/4 exactly. Can you see that? Of course you can. All right. And similarly, it doesn't really matter what the proportional ratio is. It can be anything. Okay. So if you say 0.2 divided by this number here, 0.533333, it will also be 1/4. Okay. Something happened to my left eye. Weird. Okay. So yes, so it doesn't matter which ones in particular that you use, you will get the same result. And that's pretty much it. I will give you a link to this applet so that you can download it and you can change these as you wish. Okay. And you can even move this up and down, whatever. Okay. And play around with different values. Now, what I've done is I've actually made the initial ratio, this here, 3/4. Okay. So I've made this here 3/4. And so you can play around with this and change it as much as you like, right? Much as you like. And then find what the 4 basic operations are and check them. And then you can also try to do this far more interesting one, which is given a physical unit, any physical unit, by the way, doesn't matter what it is, to produce a rod whose length is a product of phi and square root 2. Now that's something that the ancient Greek Parthenon construction workers could do, and they didn't even know how to count, by the way. And here's the irony. The greatest supercomputer today can't do this with the precision that the ancient Greek construction workers could do it with. Right? So, you've got a lot to think about. I suggest you go over this video a few times, try a few examples with GeoGebra, download the applet, study this file here, which explains to you all the details, step by step. Okay. Everything you need to know is in here. And you will understand fractions. That's the whole idea about GEORITHMETIC. It's so that you can understand fractions better than any of your ignorant mathematics or calculus professors or teachers. You could actually teach them this stuff. Wouldn't that be fascinating if you walked into a classroom and you said, hey, you know what, teach? I can do 100% precision arithmetic without even the use of numbers. So it's not tedious. It's very useful in architecture and engineering where you don't have enough significant digits. Okay, So your supercomputer basically would never even get close to the accuracy that you desire. Does that make sense? Okay, if you're not a rare subscriber to my great math channel, this new calculus channel, become a subscriber, click like, tell your friends about it, tell all the morons that you know about, your colleagues, etc., and become smart like me. Okay? This is the beginning of your mathematical career. You can become the greatest mathematician someday, just like I am today. But if you don't know this stuff, guess what? You'll never understand arithmetic. And don't fall for those idiots who say they've moved past numbers, because if you're not dealing with numbers and measure, whatever you're doing is not mathematics. Okay? It's bullshit. I am the great John Gabriel, and it is my pleasure to bring you this presentation, which I hope you will use and become smarter. Till next time.